Let's see. Hello everyone. Hopefully you can hear me. Okay. Sorry, there might be an echo for a second, but it'll go away. I'm making sure my stream is up, so I had it open in another browser window. Regardless, let me know if you can't hear me. Leave a message in the chat, but otherwise, let's proceed to talk about the probability questions that we discussed last time. So, for those of you that perhaps weren't here, I am going to briefly state the questions. So this is the last question I talked about, which is that if you flip a coin an even number of times, and just so you know, this even business will play a role here. So this is not, there's something very interesting that happens in this question because you are flipping the coin an even number of times, okay? And it's simple. You know, heads, I win, tails, you win. However, the probability of getting heads is less than a half, okay? It's less than a half. This is also very important. In the original version of this question I said you can try to analyze like p equals 0.4 or p equals 0.45, you know, just set p to be a specific number in order to aid in your in order to aid in your analysis and computations. Okay, so you're going to flip a coin an even number of times, and heads I win, tails you win, and the probability of getting a heads is less than a half. So this game is decidedly not in my favor. Hopefully that makes sense. So because the probability of getting heads is less than a half, this game is decidedly not in my favor. Now, to win overall, I have to win more than I lose. So for example, if we flip the coin 4 times, I would have to win 3 or 4 times, right? If it's a tie, like I win 2, you win 2, that's not a victory for me. So this more also plays a key role in this problem. Okay, so you're flipping a coin an even number of times. Heads I win, tails you win. The probability of getting heads is less than a half. And to win overall, you have to win more. So I have to win more than I lose. All right, hopefully that question now makes sense. Now, a couple of you in the comments were able to essentially figure out the trend here. So I'm going to show you, first of all, the algebraic side of how you might do these computations. So the tool we're going to use here to do these computations is called a binomial distribution. You don't have to have a very solid grasp on what a binomial distribution is, but it's fairly simple. I'll explain it right now. So let's say you have a particular heads-tails sequence, any particular heads-tails sequence, okay? So for example, let's say the coin is flipped twice, you get heads-heads. Assuming the flips are independent, what would be the probability of getting a heads-heads sequence? Well, that would just be p squared. If p is the probability of getting heads, then the probability of getting heads twice would just be p squared. What would the probability of getting a heads-tails be? Well, that would just be p times 1 minus p. Because the probability of getting heads is p, the probability of getting tails is 1 minus p. Right? What would be the probability of getting tails heads? Well, again, it's 1 minus p times p, which is the same as p times 1 minus p. And what would be the probability of getting, let's say, a tails-tails? Well, this would be 1 minus p quantity squared, because the probability of getting a single tails is 1 minus p. So the probability of doing it twice, you know, it would happen if you square it. Okay? So as an example, if the probability of getting if the probability of getting heads were exactly a half. So let's say this is a fair coin. If the coin were completely fair, if p were equal to a half, then the probability of any of these outcomes is going to be 1/2 times 1/2. In other words, 1/4. 1/4 for every one of these outcomes. Okay. Now let's say we want to expand this and ask the question, what is the probability of getting a specific number of heads in n flips? Okay. For example, what if you were interested in the question, you know, what is the probability of getting 3 heads, let's say in 5 flips? Well, there are a number of heads, tails sequences that have 3 heads in 5 flips. Let me write one down. So for example, you could get the 3 heads right at the start, followed by a tails, tails, right? Or you could get like tails, heads, heads, tails, heads, just as an example. So these are all possibilities for what can happen here, right? However, each of these possibilities have the same probability because getting 3 heads is going to have probability p cubed, and getting 2 tails is going to have probability 1 minus p squared. Okay, so getting 3 heads is going to have probability p cubed, and getting 2 tails is going to have probability 1 minus p squared. Okay, so now this one, same thing, right? This has 3 heads and 2 tails. So the probability of getting the first tails is 1 minus p, then the heads is p, then the heads is p, then the tails is 1 minus p, then the heads again is 1 minus p. So all in all, I'm sorry, then the heads again is p. So all in all, there are 3 copies of p and 2 copies of 1 minus p, which gives you again that the probability of this sequence, tails, heads, heads, tails, heads, is again going to be p cubed, 1 minus p squared. So if you're interested in analyzing the probability of getting 3 heads in 5 flips, every such sequence has the same probability. So all you really need to answer is how many such sequences are there? How many sequences are there that give you 3 heads in 5 flips? Well, it's just a question of where the heads occur in those 5 flips. And so the answer to how many such sequences are there is just 5 choose 3. So the answer to the question, what is the probability of getting 3 heads in 5 flips, is going to be 5 choose 3 p cubed 1 minus p squared. Okay? You can generalize this fairly easily. So if you're interested in the question, what is the probability of getting, let's say, k heads in n flips, then the answer to that question is going to be n choose k, right? P to the k, 1 minus p to the n minus k. Why? Because any sequence that has k heads and in n flips must have n minus k tails in it, right? So k will be the number of heads in such a sequence, and n minus k will be the number of tails in such a sequence. Now, the probability of every such sequence is p to the k, 1 minus p to the n minus k. And the number of such sequences is n choose k. So when all is said and done, it's going to be n choose k, p to the k, times 1 minus p to the n minus k. Hopefully that makes sense. Okay, so we're going to use this tool to kind of analyze this question. So this is the answer to the question. What is the probability of getting k heads in n flips? Okay, this is the answer to the question, what is the probability of getting k heads in n flips? All right. So what are we interested in? We're interested in our probability of winning the game. Okay, we're interested in our probability of winning the game. And remember, you win I win the game if I win more than I lose. And the coin is being flipped an even number of times. So for example, if the coin is flipped twice, well, I would have to win twice in order to win the game, right? So flips, number of wins needed. Okay, if the coin is flipped twice, then the number of wins I need would be 2. If the coin was flipped 4 times, then the number of flips I would need to win in order to win the game would be 3 or more. Right? A 2 and 2 would be a tied situation. If the coin is flipped 6 times, then the number of flips I need would be 4 or more, right? In general, if the coin is flipped 2n times, then the number of flips that I need to win in order to win the game is going to be n plus 1. Okay, so this is n plus 1 or more. Okay, so if the coin is flipped 2n times, then the number of flips that I need to win the game is going to be n plus 1 or more. Hopefully that makes sense. Now, let's take the formula that we just derived and plug it into one of these situations. So for example, what would be the probability in 4 flips of winning 3 or more coin tosses? In 4 flips, the probability of winning 3 or more coin tosses, well, this is just the probability of winning 3 tosses plus the probability of winning 4 tosses, right? So if you do this out, it's going to be 4 choose 3, p cubed 1 minus p, right? And the probability of winning 4 tosses is going to be 4 choose 4, p to the 4, 1 minus p to the 0, which is just p to the 4. In general, if you are interested in n tosses and you are interested in the probability of winning n plus 1 or more tosses, then it's going to look like this. If you toss the coin 2n times and you're interested in the probability that you will win n plus 1 or more tosses, then it's just going to be 2n choose n plus 1, p to the n plus 1, 1 minus p to the, I guess, 2n minus 1. I'm sorry, n minus 1. 2n minus n minus 1 is n minus 1. And then there'd be another term, which is 2n, n plus 2, p to the n plus 2, 1 minus p to the n minus 2. And so on and so forth it goes. You know, this is a very complicated sum. So this term in the sum, this first term in the sum, would correspond to the probability of winning exactly n plus 1 out of the 2n games, which is, you know, a winning situation for you. The second sum is the probability of winning exactly n plus 2 out of the 2n games, which is, again, a winning situation. And the third sum would be the probability of winning n plus 3 games out of the 2n. So in other words, if you add all of these probabilities up, if you add every single one of these probabilities up, that will give you the probability of me winning the game in the 2n flip game, okay? Now, I mentioned something earlier, which is that the parity here does make a difference, okay? I mentioned something here, which is that the parity does make a difference. So you can take these sums. So if I were to write them in shorthand, it would look like, you know, the sum where I goes from n plus 1 to 2n of 2n choose I, p to the I, 1 minus p to the 2n minus I. This is the probability that I win the game with 2n flips. Okay, so this is the probability that I win the game with 2n flips. So let's plot out these sums, right? Let's just plot out these sums. Let's plot out the probability that I win the game with 2n flips. So just take a quick look. Let's see here. So this is what it looks like. So I've done the evens and the odds, okay? So the probability, this is starting at a half, okay? The probability that I win the game so I'm allowing both even and odd number of flips. And you can see how differently even numbers and odd numbers behave when I do out these sums. Let me just zoom in so you can see the code in case you want to replicate this. So if you look at this, you'll see that if you set p to be 1/2, the probability the probability that I will win in an odd number of games actually does not change as you change the number of games, assuming the number of games is odd. However, if you notice for an even number of games, the probability that I win actually rises as the number of games increases. Now, this is assuming a fair coin. So this is the plot, or this is what the plot looks like if you plug in p equals 1/2. And notice I explicitly said in the question that the game was unfair to me, in which case I'm plugging in p is less than 1/2. Okay? So what happens if you shift p from being exactly 1/2 to being less than 1/2? So something interesting happens, which is these plots, they start to drop. Right? But notice the plot for the odd number of games drops in this very cleanly monotone kind of way. So it's very clear that if any number of games were allowed, then you should want to only play one game. But the situation, if you're allowed to play, if you're only allowed to play an even number of games, the plot is very different. So as you can see just by looking at this, and I think some of you in the comments did do simulations like this. I will give you how to answer the question without using any simulations. Just like if you hand me a number p, I will tell you exactly the number of games you need to play, assuming it's even. But first I want you to notice the behavior of this. So if you are allowed to play one game with a coin weighting of 1/2, that's the highest probability. If you play 2 games with a coin weighting of 1/2, that's a very low probability. If you play 3 games with coin weighting 1/2, your probability of winning is exactly 1/2 again. And if you scroll p, like if you change p, notice the shape of this graph. So for example, if you set p to be like 0.45, this graph has a max, actually. You can see the even game probability graph has a max somewhere out here. Let me change the number of points just so you can see this clearly. So let's do up to 20. So let's put in 0.45 as the probability of winning. So this is the graph. As you can see, it looks like it has a max around 10. So the probability of winning, if you're only allowed to play an even number of games, maxes out at precisely 10. And once again, I am aware that in the comments, some of you did do simulations like this and were able to get this. But of course, the question is, how would you figure this out if you didn't have like a computer and graphs to stare at? But I just wanted to illustrate this to you. So if you set p equals, let me change the plot range to be like 0.25 so that you don't see the odd case, because we've already talked about how the odd case is not the interesting one. So for the even case, if you set p equals 0.45, hold on, this plot range is to maybe 0.35. And then 0.45. Okay, so you can kind of see it. you can't quite see it. Let me put the min at 0.2 so you can really see the spike in probability at that number. So let's put that in. Put in p equals 0.45. Okay, yeah, you can really see that for an even number of games, so 2, 4, 6, 8, 2, 4, 6, 8, 10, there's a peak in your probability of winning at precisely 10 games, which then drops off later on. Okay, so once again, I got this just by asking the computer to compute these numbers, which is, a nasty sum, of course. So you can't. It is possible to massage this in a way where you can just stare at these sums. Hello, Brian. It is possible to kind of massage these numbers in a way where you can just stare at these sums in order to figure out which number will kind of maximize which number of games will maximize the probability of winning. Okay. Let me know if there are any questions about that. But now I'm going to talk about, what do you do if you don't have a computer, right? How would you figure out if you don't have a computer? Also, there's an interesting phenomenon which someone in the comments was able to figure out using a computer, which is that if you go, let's see, let's plot this here. So as you decrease the probability of getting heads in this coin, you have a drop, right? So you should play fewer and fewer games. So if it's 1/2, you should play infinitely many games, right? If it's a fair coin, you should play as many games as you possibly can, right? I should play as many games as I can in order to maximize my probability of winning. But if I drop the probability, it goes down, right? So it goes down, and the peak goes further and further to the left, so I should play fewer and fewer games. So at this point, at 0.44, it's looking like the number of games I should play should be 8, because 8 is the maximum of these points when I'm playing an even number of games. And if I keep going, at some point someone did manage to figure out in the comments that if you go past a third, so let's go to 0.33. This graph again so the graph for the even number of games again starts to max out at only playing 2 games. So past 1/3, so if the probability of getting a heads on any individual coin is 1/3 or less, you should play as few games as possible, agreeing with the intuition again. So the question is, how are you going to analyze this situation? Let me discuss this further. So I will say, if your algebra skills are good and you've stared at sums like these before, if you've worked with sums like these your whole life, then you can actually stare at these sums in order to figure it out. But let's assume that's not the case. Okay, let me just erase this and we can think through what's going on here. So let's assume that this is not the case, and you don't want to analyze these nasty sums in order to figure out these probabilities. Okay. Let's think about this plot. Okay. We want to figure out where the probability of me winning maxes out. Okay. Let's assume it does max out at some point. So, you play, let's say it maxes out at this point, 2n, right? What would that mean? That means if I play 2 more games, the probability of my winning goes down at 2n plus 2, right? Also, if I play 2 fewer games, the probability of my winning goes down, right? So if I have an honest to goodness max, that means that at 2n minus 2, I have some probability of winning. And then when I play 2n games, the probability of my winning goes up. And then when I go to 2n plus 2 games, the probability of my winning goes down again. All right. But now, how do you compare these numbers? I mean, each of these numbers is given by a horrific sum, right? So this number is, just to reiterate, it's like the sum, 2n, choose I, p to the I, 1 minus p, 2n minus I, as I goes from like n plus 1 to 2n, right? And similarly for the others. But you do not have to actually think about these nasty sums in order to figure out these probabilities. Because let's think about it. Instead of worrying about the entire sum, you should instead think about how these sums differ from each other. How do these probabilities differ from each other? Okay? So what is the difference between like, how does the probability change if I play 2n games versus 2n plus 2 games is a good question. Okay, so how does the probability change? How does the probability change if I play 2n plus 2 games instead of 2n games? Okay, this is a good question to be thinking about. So how does the probability change if I play 2n plus 2 games instead of 2n games? Well, let's analyze this situation very, very carefully. Basically, there are 4 possibilities if I play 2 more games, right? Either I was winning and I stay winning, right? I'm stacking W's. I was winning, I stay winning. Or I was losing and I stay losing, right? So at the start of 2n games, I was winning fewer than, I was winning fewer games than I was losing. And at the end, I'm still winning fewer games than I'm losing, okay? Just so you know, these two numbers are very complicated. The probability that I was winning and that I stay winning is a complicated number. Also, the probability that I was losing and stay losing is also a complicated number. But the numbers for these other 2 possibilities, which is that I was winning and now I am losing. So at the start of the 2n games, I was winning, but at 2n plus 2 games, I am now losing, versus the probability, so that's like not a hard number to figure out, okay? And also the probability that I was losing and now I am suddenly winning is also not a hard number to figure out. So the idea is, instead of focusing on the binomial distribution and, instead of focusing on the cumulative distribution of the cumulative distribution function of the binomial distribution, you should instead focus on these 2 numbers here. What's the probability that I go from winning to losing, and what's the probability that I go from losing to winning? Okay, let's think about this for a second. Let's think first about the situation that at the start of 2n games, I'm winning. Winning means I am winning more than I am losing, right? So in these 2n games, I should have won n plus 1 or more, right? So I should have n plus 1 or more victories. That's the only way to be winning at the 2n spot. Also, so I'm thinking about the situation where I go from winning to losing. So if at the end of 2n plus 2 games, I am now losing, then this means that I should have won fewer than n plus 2 games. So n plus 2, so I should say fewer than n plus 2 victories, right? Right? So if I go from winning to losing, then this means that at the start of the 2nth game, I had n plus 1 or more victories. And if now all of a sudden I am losing, then that means at the end of 2n plus 2 games, I have fewer than n plus 2 victories. But if you stare at this, you realize that this means that I need to lose. So the only way that this is possible is if at the end of 2n games, I have exactly n plus 1 victories, and that number does not go up from 2n to 2n plus 2. Let me know if that makes sense. So if I need to win more games than I lose, then for me to go from winning to losing, I need to have won exactly n plus 1 games out of the 2n games, and then I need to lose the next 2 games. Hopefully that makes sense. So what is the probability of winning? So the winning to losing probability, right? The winning to losing probability is the probability of, is the same as, to go from winning to losing, there's only one way that that can happen. The only way that that can happen is if you are winning exactly n plus 1 out of 2 endgames, then you lose the next two. All right, let me know if that does not make sense. So to go from winning to losing by playing 2 additional games, you need to be winning exactly n plus 1 out of the 2 end games, and then you lose the next 2. So what's the probability of this? Well, the probability of this is, well, basically, if I lose the last 2, the sequence needs to end in a tails, right? That's how I lose the last 2 games. And then in the first 2n slots, like in the first 2n flips, I need to have n plus 1 heads in here somewhere, right? So in the first 2n flips, I need to have n plus 1 heads in here somewhere. So the probability of getting 2 tails in a row is 1 minus p squared, right? So 1 minus p, if p is the probability of getting heads, then 1 minus p is the probability of getting tails. Since the flips are independent, the probability of getting 2 tails is going to be 1 minus p squared, okay? The probability of getting any sequence of 2n flips with n plus 1 heads is going to be p to the n plus 1 for the number of heads. So in this sequence, there must be n plus 1 heads. The probability of getting n plus 1 heads is p to the n plus 1. The probability of, and so if there are n plus 1 heads, that means there have to be n minus 1 tails. Otherwise, it wouldn't add up to 2n flips now, would it? So this is going to be 1 minus p to the n minus 1. This is the number of tails in these first 2n. And then you need to ask the question, well, how many sequences are there? How many sequences of 2n are there that have exactly n plus 1 heads in them? And the answer to this is just going to be 2n choose n plus 1. This is just the number of ways you can put n plus 1 heads in a sequence of 2n. So it turns out the probability of going from a winner to a loser in 2 additional games is exactly 2n choose n plus 1, p to the n plus 1, 1 minus p to the, I guess also n plus 1. Okay. So this is the probability of going from being a winner to a loser. So this is the probability of, I'll put this up top. Put this up top. Done. Deselect. So this is the probability up here of going from being a winner to a loser. What is the probability of going from being a loser to a winner? So let's say you're losing. So this is the, let me mark it so it's clear. This is the probability of going from a winner to a loser when you go from 2n games to 2n plus 2 games. Hopefully my slapdash notation is reasonably clear. Okay. Hopefully that makes sense. Now, so that's what this is, right? Now, what's the probability of going from a loser to a winner? So let's say you're a loser at 2n games, and then you become a winner at 2n plus 2 games. Well, in order for you to be a loser at 2n games, you need to have won fewer than n plus 1 games, right? So your number of wins has to be less than n plus 1. Has to be. And in order to be a winner at 2n plus 2 games, your number of wins has to be greater than or equal to n plus 2. There's only one way that this can happen. The only way that this can happen is if your number of wins at the 2n game mark was exactly n, and then you won the next 2 games. Okay? So using the exact same analysis, the probability that you go from being a loser to a winner is the probability that you won exactly n games in the first 2n flips. This will be p to the n, 1 minus p to the n, and then you win the next two, p squared. So, so this, if I were to simplify this, is p to the n plus 2. 1 minus p to the n. Okay. This number here is the probability that you go from being a loser at the 2n mark to going to be a winner at the 2n plus 2 mark. Okay? So now let's go back to our chart. If we want to figure out where our probability of victory chart peaks, right? So for example, if this is what our probability of victory chart looks like, and we want to find a peak, what has to be the case? It has to be the case that from this point to this point, the probability of going from a winner to a loser is greater than or equal to the probability of going from a, the other way. So if this goes up, then that means the probability of going from a loser to a winner must be greater than or equal to the probability of going from a winner to a loser, right? And then from this point to this point, it must be the case that the probability of going from a winner to a loser is greater than or equal to the probability of going from a loser to a winner. And with this analysis, you can get away from having to deal with all of the the horrific and nasty sums. Okay, so essentially, if 2n is our optimum point, then you plug 2n, and the probability of going from a winner to a loser must be greater than or equal to the probability of going from a loser to a winner. And then you do the same analysis for 2n minus 2, but in this case, the probability of going from a loser to a winner must be greater than or equal to the probability of going from a winner to a loser. Let me know if that makes sense. And like I said, this type of analysis helps you avoid the nastiness of the crazy sums, which we discussed earlier. Okay. If you're just arriving, by the way, I showed a graph of what these probabilities look like. So the top dots are for an odd number of games, and the bottom dots are for an even number of games. So you see the even-odd analysis is actually quite different for this one. The probability if you play an odd number of games just drops exactly like you expect it to. The more games you play, the worse it gets. But for an even number of games, it peaks, right? And it has this property where it's low at 2, but then it peaks and then it goes down. And it turns out that continues to be the case until the probability of getting ahead is about a third, in which case it becomes a decreasing sequence again. Okay. So this is what we're attempting to analyze here. So let's think through our analysis here. So essentially at 2n minus 2 flips, I want the probability of going from a loser to a winner to be greater than or equal to the probability of going from a winner to a loser. What does that mean? Well, that means 2n minus 2, choose n. Just plugging in the numbers in the formulas that I already got. You can double check that I'm not I'm not lying to you. P to the n, 1 minus p to the n needs to be less than or equal to 2n minus 2, choose n minus 1, p to the n minus 1, 1 minus p to the n plus 1. Okay, this is the statement that the probability of going from a loser to a winner is greater than or equal to the probability of going from a winner to a loser at the point 2n minus 2. So take the inequalities that I had up and just erased and plug in like the previous number, so 2n minus 2 instead of 2n. So this is inequality 1. Now we want the probability of going from a winner to a loser to be greater than or equal to the probability of going from a loser to winner at 2n. So for that one, it's going to look like this. It's going to look like 2n choose n plus 1, p to the n plus 1 is, let's see, and then times 1 minus p also to the n plus 1. And you would want that to be greater than or equal to 2n choose n, p to the n plus 2, 1 minus p to the n. This will take some trust on your part that I'm, not that I'm not lying to you. I'm not fibbing. I just plugged in the appropriate numbers into, hello, Pedro. I just plugged the numbers that I had into the formulas that I derived. And I'll see you later, Brian. So I just plugged the numbers that I had into the formulas I derived. And so this is the probability of going from a loser to a winner is going to be greater than or equal to the probability winner to a loser. Now, these inequalities might seem extremely ugly, but it turns out they're actually not bad at all, because there's an immense cancellation that's about to happen. Okay, why is there immense cancellation that's about to happen? Well, for one, we can assume that p is greater than 0. If the probability is equal to 0, if the probability that I win, if the probability of heads is equal to 0, then this is not a hard problem to analyze. So I'm just going to assume by fiat that the probability of getting heads is actually not 0. And if that's the case, then all of these numbers here are positive. So I can cancel, divide, do all sorts of manipulations willy-nilly without having to worry too much about these formulas. So for example, what's going to happen to this first formula after I do all of my cancellations? So let's see, put that in white. So if I take this first formula and I cancel, not the eraser. If I take this first formula and do like a bunch of cancellations. So first of all, there's a p to the n on this side, a p to the n minus 1 on that side. So that would leave just a p here, right? There's a 1 minus p to the n plus 1 and a 1 minus p to the n on this side. So you do a quick cancellation. So that would leave a 1 minus p on this side. Okay. Now, what does 2n minus 2 choose n? Well, there's 2n minus 2 factorial in the numerators of both of these expressions. So those will also cancel out, right? Then in the denominators here is n factorial, n minus 2 factorial for this one. And for this one, it's n minus 1 factorial, n minus 1 factorial. Okay? So that means there is an n over here. And this is an n minus 2 factorial, n minus 1, which means there's an n minus 1 over here. How nice. Come on, that's pretty nice. Like you just, everything kind of melts away very, very nicely. And of course, if you missed the wins to losses, losses to wins analysis, this will all seem like insanity to you. But we're almost done with this problem. We can move on to the next one. And so for the other one, the losses to wins analysis, you'll get basically that if you do the same cancellation for the second one, you'll essentially get that whatchamacallit. Let's see here. So you would get, wait, I hope I didn't mess up this. So you do the same cancellations. You would get a p on this side, right? And then you would get a 1 minus p on this side over here. And then you would get an, let's see, 2n n minus 1. So you would get n times 1 minus p is greater than or equal to, hold on, I think I may have messed these up. Just give me 1 second to verify. So let's start with the first one again. So after I said the cancellation is immense, but I guess it's important to keep track of what's going on here. Let me make sure I wrote these down correctly. So it's p to the n, 1 minus p to the n, that's correct. 2n minus 2 choose n. 2n minus 2 choose n minus 1. and then p to the n minus 1, q to the n plus 1. That's right. 2n, choose n plus 1, p to the n plus 1, 1 minus p to the n plus 1. And this is greater than or equal to p to the n plus 2, 1 minus p to the n, 2n choose n. Yeah, I wrote them down correctly. So let me make sure I'm canceling correctly. So there's going to be a p on this side from this cancellation, less than or equal to a 1 minus p on that side. And so now the issue is like what's left over from the binomials. The 2n minus 2 factorial will cancel with the 2n minus 2 factorial. And in the denominator here, let me write it out instead of trying to do it in my head. This is going to be n factorial, n minus 2 factorial, and this is going to be n minus 1 factorial, n minus 1 factorial. All right, so you put the n over here, you get n times 1 minus p here. This cancels that. And then you put the n minus 1 over here. You get n minus 1 times p. I think that is accurate. And then you do the second one, which is, let's see, 1 minus p is left over here. This is greater than or equal to, there's a p left over here. And then there is, this is over n plus 1 factorial, n minus 1 factorial. So you'll get, I believe, an n here and an n plus 1 here. Okay, that's, sorry, I just started second guessing myself over there. Does this mean assuming not only that p is not 0, but also that it's not 1? Well, p can't be 1 because I started the problem saying that the game was against me because, p was less than a half, right? So a technical point, but, you can just assume that p is less than 0. So, if you play with these for like a hot second, and I think I've spent long enough on these, you'll get the following inequalities. If you just put all the n's on one side, put all the p's on another side, and you will get the following, which is that 1 over 1 minus 2p minus 1 is less than or equal to 2n, which is less than or equal to 1 over 1 minus 2p plus 1. So it's just algebra that gets you from here to here. You can just trust me, or feel free to do the algebra yourself. And so essentially, 2n has to be between 1 over 1 minus 2p minus 1 and 1 over 1 minus 2p plus 1. So, assuming 1 over 1 minus 2p is not a, I guess an odd number, an odd whole number, 2n is just the integer between the even integer between 1 over 1 minus 2p and 1 over 1 minus 2p minus 1 and 1 over 1 minus 2p plus 1. And that's it. So using this, it's very easy to solve for the optimum number of games that you need to play. So for example, if the probability of winning, if the probability of heads is 0.4, right, then this number 1 over 1 minus 2p is 1 over 1 minus, 0.8, which is 1 over 0.2. 1 over 0.2 is, I believe, 5. So 5 minus 1 is 4, right? So it would have to be an odd number between, 2n would have to be an even number between 4 and 6, right? So you should play 4 games here. And if it's like 0.45, let's try 0.45. If p is 0.45, then 1 over 1 minus 0.45 is 1 over, so this is 0.9, right? So this is 0.1. So this is, you should play 10 games in this situation. So not bad at all. So all this messiness with all the all these probabilistic graphs gives you a very simple formula for the number of games that you need to play that will maximize your chances of winning. So I hope you enjoyed that one. I love this problem because it is so alarmingly counterintuitive. All right. Let's move on to the next problem, which was the Gladiator one. And then I also want to share something interesting with you, which is about, well, I don't know how much time we'll have. We'll see how it goes. So let's talk about the Gladiator problem. So if you weren't here and you don't remember the Gladiator problem, I'm going to describe it again right now. So I have a bunch of gladiators. Their strengths are, let's say, whole numbers. So this is my Gladiator team. I'm writing down their strengths. And you have a Gladiator team. You can write down their strengths. Make sure they're the same. 1, 2, 3, 4, 5, 6, 7. Okay. This is my Gladiator team. This is your Gladiator team. And the way these matchups work is simple enough. So let's say I put up my Gladiator with strength 8. And you put up your Gladiator with strength, let's say, 50 to meet my Gladiator of strength 8. The probability that I win is going to be 8 over 58. So just add the two numbers. It's going to be 8 over 58. The probability that you win, because you sent out a much stronger Gladiator, is going to be 50 over 58. Okay? The probability that I win, 8 out of 58. The probability that you win is 50 out of 58. So the probability that you win is going to be much higher, which should make sense because you sent out a much stronger Gladiator. However, you know, to the brave often comes victory, because if I happen to win, then my strength 8 Gladiator becomes a strength 58 Gladiator. So I consume, you can think of this as an increase in confidence. So I will consume the strength of your Gladiator. And my Gladiator will become strength 58, and your Gladiator's dead, gone. Okay, so that's the situation that we find ourselves in. And so the question that I asked you guys, or the question that I wanted you to think about, was what is the optimal strategy in this game? What order do you send out your Gladiators in order to maximize your chances of victory? Okay. That is the question here. And I made the claim, a rather shocking claim, that it actually does not matter. It does not matter. Your probability of winning is the same regardless of the order that you send out your Gladiators, which is kind of insane, right? So why is this? Well, if you're paying attention when I was talking about martingales, this is an example of one too. So this is a perfectly fair game. So this is another example where if you have a game, there's some technical properties, but if you have a game that's perfectly fair, you cannot expect to win more than what you started with, regardless of your strategy. So this is another example of a martingale, but I'm not going to analyze it that way because I already did, you shouldn't show the same trick twice. So I'm just going to analyze it a little bit differently so that, you get to see a slightly different type of analysis. So let's take a look at this. Here's what I want to ask you. I'm going to analyze this with expected values. Expected values are a fantastic way to analyze games. It doesn't always work. I'll give you an example of a situation where it would be a bad idea to analyze a game with expected values. But they're a great way to analyze what the fair price of the game is. Okay? Why is an expected value a good way to analyze what the fair price of a game is? Well, here's how you usually compute expected values. If you have no other insight, if you just want to, grit your teeth and compute an expected value, here's how you would do it. You would write out each possibility in the game, and you write out the probability of each possibility. and then you do the weighted average of the two. Okay. So for example, if I'm rolling a die, there are 6 possibilities. I can get 1, 2, 3, 4, 5, 6. Okay. What are the probability of each possibility? It's a sixth, right? I multiply each possibility by its probability. I add the whole thing up. That will give me the expected value for this game. Okay. In the case of a die, the expected roll is 3.5, just the average of the numbers 1 through 6. I hope I did that right. So the expected value of the roll of a die is 6. So for example, let's say I I gave you a game. Let's make it a little weird. Let's say let's say I try to flummox you in some way, and I say to you, all right, if you get 2 heads in a row, I'm going to give you $10. Okay, and if that does not happen, so let's say I flip coin twice. I'm only flipping the coin twice. If you get 2 heads in a row, I give you $10. But if it doesn't happen, you need to give me $5. So you lose $5 in this situation. What would be a fair price for this game? What would be a fair price for this game? So let me know if the game makes sense. So I flip a coin twice. You get 2 heads. I hand you $10. Any other circumstance, you hand me $5. What would be a fair price for this game? So the question is, what is a fair price for this game? Question mark. Okay. Matan Levy says, do we want to maximize profit or the number of wins? Because the probability of winning can differ even if the expected value says 0. Well, in this game, it's winning and maximizing profit is the same because we're only playing the game once, right? So I understand your question, but I'm gonna just I'm gonna skip it for a second. So in this situation, I just want to make it as simple as possible, just so we can think about what information the expected value gives us, right? That's all. And then we can talk about more complicated situations in just a moment. Okay. So what is your expected winnings of this game? Well, if you do an expected value analysis, it's fairly simple. So if you do 2 coin flips, there are 4 possibilities. There's heads heads, tails heads, heads tails, tails tails, right? Each possibility has a probability of 1/4, right? So let me move things over here. And I believe ZQ Limmy already has the answer, but let me catch up real quick. So each of these possibilities has a probability of 1/4, right? So, but in heads heads you win $10. In tails heads you lose $5. Heads tails you lose $5. Tails tails you lose $5. Okay, so in this case, it's your expected winnings. So your expected, I should say, like your net, right? The expected value of your net is going to be, I guess, -5/4, which is -$1.25. I guess you were slightly off, ZQ. Let me. So if you're doing an expected value analysis, like this is like the simplest casino in human history, you should be paid $1.50 in order to play this game, in order to make it fair. This is not a fair game. Okay, a fair game is one where the expected value is 0. So you can use expected values to very quickly kind of analyze games, because you just take all the possibilities in the game, the probabilities in the game, and this can be hard to do, especially if there are an infinite number of possibilities. But we'll get to that in a moment. So in this situation, you should be paid $1.25 in order to play this silly game that I've constructed. Okay. Now, expected values are a fantastic way to figure out the fair price of a finite game. Okay. be careful using expected values on more complicated situations. So for example, you can't use expected values to analyze like stock prices and things like that. It's not so easy. And the first person to kind of, I think it was Bernoulli, who analyzed one of the first paradoxes that comes with using expected values to analyze games. So I just want to take a brief moment to discuss the St. Petersburg paradox. Just so you are cautious when using expected values in your day-to-day life. All right, I'm going to play a game with you, okay? I'm Mr. Big Money over here, and here's what we're going to do. So you start flipping a coin, fair coin. So flip a fair coin. Okay, flip a fair coin. When you get ahead, I'm going to hand you some money. Okay. And when you get it, the first time you flip heads, I'm going to hand you some money. Okay. That's the game. The later you get the head, the more money I'm going to hand you. Okay. So the later you flip the head, the more money I'm going to hand you. So here's the situation. If you flip heads on the first flip, I'm going to hand you $1. If you get it on the second flip, I'm going to hand you $2. How about that? If you get it on the third flip, I'm going to hand you $4. Okay? In general, if you get heads on, let's say, the nth flip, I'm going to hand you 2 to the n minus $1. A lot of money. Okay? So for example, if you flip heads on, like, I don't know, the quadrillionth flip, I don't know what that is. I'm going to hand you a sum of money that's, I don't know, it's probably like greater than the atoms in the universe. Don't quote me on that. There's just some, very, very quickly your winnings become absurd. But at the same time, you have this intuition that that's probably not going to happen. I mean, come on. So like you start flipping a coin, like how, like it's not going to happen very often that, you'll flip. You'll get like 100 heads before you hit your first. Also, I flipped my. Talking about coins, this should say tails, heads, not heads, tails. Okay, let me ask you guys a question. How much money would you pay me to play this game with me? Okay, so that's the question. How much money would you pay me in order to play this game with me? Okay, there's a potential for a lot of money. Let me know your answers in the chat, if you care. So how much money would you pay me in order to play this game with me? So you get ahead on the first flip, I hand you $1. You get it on the second flip, I hand you $2. You get it on the third flip, I hand you $4. You get it on the nth flip, I hand you 2 to the n minus $1. Okay. So for example, if you got the head on the 11th flip for the first time, I would hand you $1,024, for example. So what do you think you would pay me to play this game? $42. Good answer. CQ Limmy. Any other answers? Okay, people are shy today. Maybe they don't want to venture guesses. I will say this to you. According to an expected value analysis, the fair price for this game is actually infinite. Okay? Why? So let's just do an expected value analysis. Okay? Let's write out the probabilities and their possibilities. So what's the, Matan Levy says about $2, I see. It's a good answer. So what's the probability that I win $1? About a half. I mean, no, exactly a half. The probability that I win $1 is a half. The probability that I win $2 is a quarter, right? So I win $1 if I get heads on the first. I win $2 only if I get a tails heads situation, right? I win $4 if only if I get a tails heads situation, and this happens with probability 1/8, right? Tails heads happens. So that happens, I win $8, and that happens with probability 1/16, right? So if you do an expected value analysis over here, each possibility times its probability is always going to be a half. Half, 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 forever. You add 1/2 infinitely many times, and you get, it doesn't converge. It goes to infinity, right? So according to expected value analysis, you should empty out your bank account. You should take all the money you have to play this game with me, and it'll be worth it for you. Which please don't do that. That is a bad idea. So what's wrong here? A lot of people have said a lot of things about what's wrong here, and I think the consensus is that money's a little funny. So what Bernoulli and I think even economists use to this day is this idea of a utility function to resolve this paradox. So you can resolve this paradox by considering the fact that, if you're all the big prizes concentrate at a very improbable event, that's true, but the amount I hand you for that improbable event is a lot, right? I will say this game is a lot fairer than the lottery is, The lottery has negative expectation for you, right? So this one's a little counterintuitive. Actually, the odds are in your favor if you play this game. And the odds are in your favor no matter what you bet on playing this game, right? So that's what makes this a paradox. I mean, it's very counterintuitive at the end of the day. You should, an expected value analysis on the lottery will quickly reveal to you that the lottery is never worth playing. An expected value analysis on a casino will quickly tell you that a casino is not worth going to, except for entertainment, of course. But this one, the expected value analysis fails, okay? And the way this paradox has been resolved is with something called a utility function. I wouldn't say it's resolved, but one of the ways to think through it is something called a utility function. The idea of a utility function is, if you have, but I won't live to see those prizes. Okay, I guess that's another way to resolve this paradox. But I'll tell you the way that the economists and whatnot deal with it. The way they deal with it is, money does not scale like linearly. Like if you were actually a billionaire, winning another billion is not going to mean as much to you as going from like a thousandaire to a billionaire. Right? So the reason you should not empty out your bank account to play this game, even if it were possible to instantaneously flip a coin any number of times. Okay? So even if you were able to resolve this I won't live to see the prizes that Matan is pointing out, even if it were possible to instantaneously get the answer to what the amount of money you win is, it would still not be worth it to play this game because when you're broke, money means a lot more than you're rich. That is the idea of a utility function fundamentally, and that's what Bernoulli came up with. So it's an interesting concept. Maybe we can talk about it some other time. But regardless, I just wanted to point out some of the issues with using expected values to analyze games, as we are about to use expected values to analyze the Gladiator game. Okay, so I'm gonna use expected values. It's going to be very powerful, of course. It usually is, but I just wanted to caution you before I did it to be careful in your life using expected values. So, and by the way, if you use expected values to analyze like options prices or something, then it's vulnerable to some St. Petersburg-esque shenanigans. Another point. Well. So QCXCQ, are you a fan of XQC? so that is a good point, but actually that's kind of wrapped into the utility function, right? So money, arbitrary, like as the sum of money gets larger and larger, it's not like a linear scale, right? So just the idea that, at some point, certain amounts of money just become like impossible. You can wrap all of those ideas up into a utility function, potentially. Okay. In any case, let's say you come up with your amazing strategy for this Gladiator game. So I have my strategy. I'm not going to tell you what it is. Okay. I have my amazing strategy. Okay. You have your amazing strategy. I have my amazing strategy. Okay. Let's try to figure out the probability of victory with my strategy. Okay. So here's what I'm going to do. Let's say I win. Okay. So there's two possibilities. I win or I lose the Gladiator game. Agree? I win or I lose. Those are the possibilities for the Gladiator game. So if you win the Gladiator game, how much strength are your gladiators left with? What is the total strength that your gladiators are left with if you win the Gladiator game? Well, let's say I start with a total strength M. Okay. Let's say you start with total strength N. So far, so good. So I start with total strength M. You start with total strength N. If you win, then you will walk away with total strength, adding up all the strength of your gladiators as M plus N. Agreed? And if you lose, then you're going to walk away with the total strength of your gladiators being 0. Does that make sense? So if you win, you walk away with total gladiator strength M plus N. And if you lose, you walk away with total gladiator strength 0. This is true regardless of the strategy that you pick. Okay. Now, I don't know the probabilities that this is going to happen, but let's say you win with probability P and you lose with probability 1 minus P, where P is some unknown number. I don't know. Your strategy gives you some probability of victory, P, and some probability of loss, which is definitely going to be 1 minus P. It's just that with your strategy, I don't happen to know what this number is. Okay. Now let me ask you another question. Every matchup, how much strength do you expect to gain or lose in every matchup? So in every matchup, let's say you pit, let's say I pit my gladiator of strength X against your gladiator with strength Y. Cat's moving my camera. So let's say I pit my gladiator of strength X against your gladiator of strength Y. Well, let's analyze this situation now. So I need a little bit of room. So now let's do the expected value analysis for just a single match. Okay, so just a single match. So for a single match, let's say I win, right? So what is my expected change in strength, right? So my total, if I pit a gladiator of strength X against your gladiator of strength Y, I have the potential to gain strength Y, right? If I win, I'll gain your gladiator strength into my total. And if I lose, I will lose X from my total gladiator strength. Right? So this is the analysis. So this is the analysis for the entire strategy. And up top here is just the analysis for a single game. Okay? However, what is the probability that I win? The probability that I win is X over X plus Y. Right? What is the probability that I lose? The probability that I lose is Y over X plus Y. So what is the expected value? What is the expected gain or loss in strength in a single match? Well, it's yx over x plus y minus xy over x plus y, which is 0. So in every single match, no matter what I do, the expected gain or the expected gain in strength for me is 0, right? So no matter my strategy, regardless of how I structure things, every single match, the expected strength gain or loss is 0. Which means, regardless of strategy, my expected strength when I leave the arena is going to be the same as my strength when I came into the arena. Okay, so you know that the expected, so for me, I came in with total strength M, right? I came in with total strength M, which means when I leave the arena, regardless of strategy, I'm going to leave with an expected strength of M, which means that P times M plus N plus 0 times 1 minus P, this is my expected strength when I leave the arena, should equal the expected strength, the strength that I had when I came in the arena, because no match changes my total strength. So this is just going to equal M, which means my probability of winning is M over M plus N, regardless of my strategic decisions. And your probability of winning is N over M plus N, also regardless of your strategic decisions. It's kind of insane, right? I don't know, I find that quite beautiful. So I have a challenge question for you, if you choose to accept it. How does this analysis change, or how do you analyze the situation when there's no boost in strength for the gladiators? Okay, so what happens when, so let's say my gladiator of strength 5 beats your gladiator of strength 3, my gladiator stays at a strength of 5. So there's no corresponding increase in strength. This is a much harder problem, so be extra careful with it. What is the optimal strategy in that situation? And yeah, that's exactly right, Matan. So the probability of winning absolutely does not depend on strategy. So anyways, I hope you guys enjoyed those solutions. I'm trying to think if I should do anything else, but you know what? It's fine. Maybe I'll leave it at that. Thank you to all the people who showed up. I truly appreciate it. I hope you enjoyed the stream. I hope you enjoyed the solutions. It is crazy to me that it does not depend on, and also XCQ, XQ. You commented that you weren't able to figure out like a proof for why, like what happens when the probabilities change in problem 4. You notice that if the probability of winning was 0% strategy, 100% skills. You commented that if the probability of winning goes down to a third, then the optimum number of plays is 2. But if it's between a third and a half, it's somewhere between 2 and an infinite number of plays. And earlier in the stream, we were able to derive a formula that showed you the exact number of plays. So if you go back, you can see that your question is answered. In any case, I think that's all I have to say. So I hope you guys enjoyed this. Yeah, that's it. Peace.